All right, guys, hopefully this will be a shorter video. Our lecture on this little part is on mass spectrometry. There's lots of little multiple choice questions that are dealing with this, and then a few for response. So first of all, we need to figure out what a mass spectrometer is. Now, this is a device that determines the mass of atoms or molecules and isotopic composition. So you might have forgotten what an isotope is from your previous chemistry class, but an isotope has a different mass because of different number of neutrons. So for instance, you have carbon 14 and carbon 12. Well, carbon 14 has a molar mass of 14, but carbon 12 only has a molar mass of 12. Now, the reason why these have different molar masses is because of the number of neutrons that you have there. Remember, when we get the atomic mass unit, we have protons plus neutrons. So neutrons has a big role in the mass that we have. Now, have you ever wondered why we have masses on the periodic table that are not exactly 12 or not exactly 14, or we have iron that's 55.85? Well, the reason why is because what we do is we take all this isotopic composition and we take the average atomic mass. So it's all depending on what's more abundant on the earth and things like that. So that's why you don't see any molar masses on the periodic table that are nice even numbers. Now, how a mass spectrometer works is there's mainly four main sections that we have here. So this first section, you put your sample in, and it goes through an electron beam. What this is doing is ionization. So this is our very first stage here. We ionize our sample. Ionization means that we are knocking off electrons. Now, once we have these electrons knocked off, it's now positively charged. So if we have an electric field, that electric field will accelerate the ion that we have present there. So that's stage two. Stage two is acceleration. Once we have that ion accelerating through here, we now have stage three, which is interacting with a magnetic field. Once it interacts with a magnetic field, those ions are going to be deflected. And they're going to be deflected according to their mass. So think about it. Least massive ions are going to be deflected more because they have less mass. More massive ions are going to be deflected less because they're more massive. If I try to, push something that's very, very heavy versus push something that's very light, the thing that's very heavy is not going to go as far. So this should make pretty good sense to you guys. Our last stage here is detection. So now that we have these deflected, they're kind of separated out according to their mass. We then have a detector that gives us some pretty special data. So now that we know how a spectrometer works, the question is, how in the world do we get data and interpret that data? So this that you see right here is data for an isotope, the different isotopes of neon. So you'll get an ion beam intensity, so that's your detector, and versus the mass number. And so you see how we have three little humps here. We have 1, 2, 3. Okay, so what does this tell us about neon? Well, when I look at this data, I would say, okay, well, we have a peak at mass 20, a peak at mass 21, and a peak at mass 22. That must mean that neon has three different isotopes. It has an isotope with a mass of 20, an isotope with a mass of 21, and an isotope of mass 22. What I also should be able to detect from this is that the the isotope of neon 20 is most abundant compared to the others. Now, this data will be translated to this. This is the type of data you'll see in the question for AP, multiple choice, or even maybe free response. So instead of having the ion beam intensity, you'll see relative number of atoms that's here versus the mass number. So this is translated to how abundant that isotope was in that particular sample. So you see that isotope 20 has a mass or abundance of 91%, we could translate that to. 21 has abundance of 0.3%, and 22 has an abundance of 9%. So what we can do is we can take this data and we can actually calculate the mass that we have on the periodic table. And I have the equation here. So what we do is to find the average atomic mass is the mass that you see on the periodic table. So for instance, like we talked about iron having 55.85. This formula is how I find that number 55.85. So average atomic mass, the mass that you see on the periodic table, is equal to the percent abundance of one isotope times the mass of that isotope. So what I would plug in here for our example, the percentage would be 91% times isotope 20 plus the percentage of your next isotope, so that would be 0.3% times the mass of that isotope, which would be 21. If I have more than two isotopes, I just keep continuing with this equation. I would add percentage of the last isotope, 9%, times the mass of the isotope, which is 22. When I take those values and I add them all together, then you get the average atomic mass, which is the mass that you see on the periodic table. Okay, so here's an example that we have of something that you might see. We have the average or relative atomic mass of natural copper using the mass spectrometry data below. The mass values for copper 63 and copper 65 are 62.93 AMU and 64.93 AMU respectively. Now, whenever you see this where the little mass is on top, this is an isotope. So this is copper 63 isotope, and this is copper 65 isotope. So copper 63 isotope has a mass of 62.93, and copper 65 isotope has a mass of 64.93. So if we look at this data here, which isotope do you think is more abundant? Is it copper 63 or copper 65? You should have said copper 63 because this is 69.09% abundant, and this one is only 30.91. Another question that they can ask is, what is the average atomic mass? So if you wanted to figure out the average atomic mass, then you can just simply use the equation I showed you before, where we take the percentage times the mass plus the percentage times the mass, and we get that value there, and that should equal up to what we see on the periodic table. So another hint that you can do is when you're working with these in multiple choice, use that periodic table to help you answer these questions, because these should be relatively easy questions and you should be guaranteed points from there. There's one more thing I want to leave you with. Now, we talked about using that equation. The average atomic mass is equal to the percentage times the mass plus the percentage times the mass. Now, this is if you're trying to find average atomic mass. But my question to you is, what would we do if we knew the average atomic mass, if we knew the mass on the periodic table, and we were trying to find both of these percentages? That's my question for you guys, okay? I want you to ponder on that and bring your ideas to class tomorrow. What would we do if we knew the average atomic mass and we were trying to find those percentages? We weren't given this data or anything. All we were given was that we have copper 63 and we have copper 65 and what its molar mass is, according to the periodic table. So, a couple of things I want you guys to do. First of all, tell me how you would find these percentages, all right? That's what we just talked about. Secondly, I want you to get practice, and I want you to determine the average atomic mass using this data here so you can practice with those calculations. I'll see you, and hopefully you'll do well.